So this is Jan from Simpletree. This is tutorial 2. From tutorial 1 we already know how to produce such a tree model. There is some differences. Um, so the curvature is already pre-computed. So we have the stem and the major branches detected. And what I did differently was the parameters. So here are quite large parameters, um, and we still ignore this part, but this results that my model still a lot is detected, but we see here a lot of overestimated cylinders. Also, in the next when I would press here compute now, we would go to this allometry dialog, you know, from tutorial 1, and this time I did not use the allometry approach. So these cylinders here, they are really large, and these are these points here which don't fit so well into the equation. So what can we learn? This model might be still appropriate, and so even if we have a large volume overestimation because of these heavily overestimated cylinders, we could correct this. So let's assume we don't know the allometry parameters from tutorial 1. So we would press this button here to write the CSV files. Then here in this folder we can just do it. So in this folder now we have like 5 files with the name of the loaded point cloud, which is cherry1, and we can use this first file, which is tagged with detailed, in R to compute the allometry parameters. So I have already here a script. So what I did was copy those 5 files and put in this subfolder. Sorry, I'm sick a little bit. So this links to this subfolder I just created. We have here R, and I look for all files which have this detailed contained in their names. So when we go back, there is just one file. If I would have modeled multiple trees, there could be more files. And then you can look through the code, but here is some fitting routine, and here I give the file name where I want to save my file, and yeah, so now I just run the R script. You can get it from my homepage or contact me. So now this file was generated and stored on my desktop, and yeah, it's already a little bit here denoised. So we have fitted this power function with parameter A and B, and so if we go back to Simpletree now, so it's 45.045. We can either do the allometry directly in the modeling or by using this button. So it was A was 45.045 and B was 2.431. 2.431. So now we have 240 liters. And I press now. So this parameter, it's half a centimeter, 2.5 millimeters. Uh, Whatever this allometry correction does, twig will never get smaller than half a centimeter diameter or 2.5 millimeter radius. So we lost 60 liters of biomass volume. I mean, and this is a good, because this model looks really much better now. And it did correct all these overestimated cylinders. Yeah, I would never expected this, that these cylinders, yeah, that this makes so much different volume, but there's not only my publications or the one of me and my co-authors. There's also other publications which hint to that twig volume is overestimated, and Pazzi Ramon, for example, had also developed an independent statistical approach to correct those cylinders as an example. So yeah, this model looks really good. So I could press now again. So cause we have a better model now with this correction, and I would be quite satisfied. So with this, um, I regenerated the comma separated value files. So they are stored in the output folder. They have the same name now. It's still the same name of the point cloud. I put it here again in the folder, but into another subfolder. So I go back to R. I extend this path to link to the new models. We will get slightly different parameters for sure. I give it also another name, and I rerun the script. And now on my desktop, this file. So we have here, excuse me, these have been the old parameters. And these are the new parameters. So this is the improved model. So, and of course we can predict the now by measuring, let's say the important diameter is not the dBH like in classical forestry. It's if we look for this diameter, it's diameter at ground level, the lowest cylinder, the root cylinder diameter. This might be the dBH one. So, and on the y-axis we have the predicted volume, which is 166. And now we could use this to predict other cherry trees. And so we could convert by multiplying with the density value to RGB, and maybe even if you think it's worse and you did multiple trees with similar allometric models. I never did this until now, but this is a great site where you could store such um, stuff. And normally you need multiple hundreds of trees to predict such a function. But if we look one more time, this is quite a decent number of measurements already from a single tree, and you could just use 10 and have a lot of information, which makes it statistically more significantly. And so for the globe allometry page, we would should convert this radius parameter to diameter parameter, and this needs to be multiplied with density also. But I think more or less this is a good estimating also for classical measure DBH and predict the RGB of a tree. And yeah, that's one thing. So I will end tutorial 2 here. Tutorial 3 will be quite short.